Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. So, what are we doing today? Thank you so much for asking. Let's go ahead and open up Zernal PP and let's just get going. Okay, so, okay, as of yesterday, we were talking about this. We had this research paper, right? Let's talk about it really quick. So, we were going through this paper yesterday, and there was a lot of rigorous mathematics that I don't understand, but I went through it a bit more after stream just to make sure that I understood the stuff that we were talking about yesterday. And I started realizing something. I feel like the paper basically only acted, okay, its numerical results, which are the only results I could analyze, essentially went through a subset of problems, of Sierpinski problems, right? Okay, here's the issue. I am wondering how general the results are of the paper that we were working at yesterday. Does it work on other attractors, like, for example, the Barnsley Fern? Now, obviously, Barnsley Fern, very simple fractal, but it acts fundamentally differently than the Sierpinski gasket, you know? And so I started getting into this idea, this question of, okay, well, if we have a subset of Sierpinski triangles, right, as the primary thing that the paper is acting on, let's just do something else. Let's do another attractor and let's see if we can replicate the results of the paper on another attractor. We're still trying to answer the question of how do you know if you're attracted to the Sierpinski triangle versus another attractor. So how do you know if you are attracted to the Sierpinski triangle versus some other attractor, right? So that's what we're trying to answer, and I think we're getting there one step at a time. So what I decided to do was actually take a step back. Again, take a look at the Barnsley Fern today. That's not what I meant to do. Take a look at the Barnsley Fern today. And in looking at the Barnsley Fern, hopefully we can produce a visualization for it that people haven't shown, and I don't understand why they haven't shown it. And yeah, we can just kind of make a nice visual that people haven't seen of the Barnsley Fern before, and then go from there. So that's kind of my goal for today, just to kind of revisit the Barnsley Fern in light of some of the stuff that we were talking about yesterday, and go from there. Again, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. I am unfortunately only able to stream for 2 hours today, so no workout today, but tomorrow, happy to say, we will probably be going back to doing some of the workout stream stuff. And doing that. So tomorrow I'm hoping to do a longer stream, like honestly, like 6 or 7 hour long stream, and go from there. Fortuitous Lover, hey, how are you? I'm having a wonderful day. So let's just go ahead and hop right into it. Journal. Actually, fine. Let me just scroll down. We are talking about a general class of fractals that can be created via something known as an iterated function system, which is going to be notated as IFS. Here, the idea is that we have a number of different functions, and I'm going to show you the functions for specifically the Sierpinski triangle. So we have function 1 is going to be equal to some sort of point plus some sort of position A over 2, where we have 3 positions. I'm butchering this, and C. Function 2 is going to be equal to P plus B over 2, and function 3 is going to be equal to P plus C over 2. The idea is that each of these functions will bring you halfway towards one of their points, A, B, or C. If we start at with some random point in space, let me do that in light green over here, and we have it choose one of these functions at random, it will move towards one of these 3 points. So let's say halfway towards A. It can then choose one of those functions at random again, so it moves halfway towards B, halfway towards C, so on and so forth. And eventually, if we just follow this point for, I don't know, 1 million, 2 million steps or something like that, we'll start to see the Sierpinski triangle form underneath. Now, I do have visuals of this. I'm just not going to show them here. I mean, unless people specifically want to, look at it. But yeah, so that's kind of what we're doing here. We're creating the Sierpinski triangle through, selecting a random point and selecting a random movement function every step, and then doing like 1 million different steps. There's a lot of really interesting questions here that people have definitely talked about and looked into. And then there's a bunch of questions that people apparently didn't look into. Like, for example, how do you know exactly how far this point is from the Sierpinski triangle for any given point? That apparently has not been solved for years, like literally decades, until like a few months ago by this mathematical paper that we found. And honestly, like I just don't know if we need to go through the results a bit more detailed. I'm not saying that the results are wrong. I'm saying that I'm a bit worried about the generalization of those results to other fractals. That's what I'm going to say. And that's what I want to test. So we're just going to kind of, I don't know, look into that. So the key to the iterative function system is that it's basically built of a bunch of different functions. Here, these sometimes called the Hutchinson operator. Operator, which is a combination operator, which is a combination of a bunch of different functions in order to create this one operation. So like all three functions together is the Hutchinson operator. So if we create a different set of functions, we can create, in effect, a different fractal. And that's kind of the heart of the Barnsley Fern. The idea here is that instead of using this set of fractals, this set of functions, we use a different set. And that different set is, let me just Google it for you, Barnsley Fern, perfect. 1 second, is this set in here. Okay, now what you might notice is, if you happen to watch my video on affine transformations, is that these are all affine transformations, which is why I did the video on affine transformations, so we could talk a bit about the Barnsley Fern and other fractals and stuff like that. So now that we do have a visual for affine transformations that I think is pretty good and pretty crisp and clear, we have a visual for iterative function systems, again, pretty crisp and clear and understandable. I want to put them together and talk about the Barnsley Fern. So that's what we're going to do. I have a few, like what I want to do is like visualize each of these affine transformations separately. The thing is, a lot of people have done the Barnsley Fern before. It's super common, like everyone does the Barnsley Fern. But the thing is, I feel like very few people have a good visual understanding of it. I think a lot of people have like, I don't know how to put it, but they kind of like forego the visuals of each transformation and just say, oh, this transform is for the stem and this transform is for the leaf. But it's like, you can't just tell me that this transform is for the leaf or this transform is for the stem or this transform is for this part of the fractal without showing it to me, right? You can't, it's like one of those classic cases of like show, don't tell. And yet people for some reason just haven't grasped that. So I kind of want to combine a couple different things here. One, I want to show what each of these transforms do. And two, I want to do that same visualization I did with the affine transform where we have the little bars moving up and down for the Barnsley Fern as well, and show how the fern changes depending on how these transforms change. That's what we're doing. So let's go ahead and hop into a visualization. CD projects, Simuleos fractal. L is here, VI Sierpinski .mpv. Actually, let me see what we have here. I have a Barnsley.cpp. Because clearly I do, right? I apparently was doing this before. So let me just see what happens if I do, if I just run this. What do we get? So I'm going to do CD projects, Simuleos, fractals. L is here. And let me just run G++. Nope. Try this again with a lowercase g. Perfect. And then we can change that to Barnsley instead of Sierpinski. And then hopefully we can get a Barnsley Fern visualization. Bada boom, bada bam. Done and done. Barnsley, and then Barnsley.cpp. Okay, give that a go. Run /Barnsley, see how long it takes. I don't think it'll take too long because we only have 20,000 points. And then we're just going to see what it looks like and go from there. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. I only have 2 hours to stream today, so that's why I'm kind of going through things quickly. But clearly, again, if you do have questions, just ask. Yeah, I'm going to also do something really quick to my side screen while this is running. Give me just a second. My, for some reason, my browser was really acting up, and it wasn't really showing me all the results that I wanted. Okay, so that's done. Let's run mpv temp video.mp4. There's the fern. Perfect. It actually looks pretty good. Okay, let's go over here really quick. Over there. Perfect. And here. Okay, I don't know why, but it's fine. Okay, so I'm going to open up a new terminal, and we're just going to have the fern just showing in the upper left-hand corner of the screen so people know what we're talking about. mpv loop 0 temp video.mp4. Up there. Perfect. Great. And now we can just go ahead and hop into it. Let's see, what do I have? And again, just feel free to ask any questions. The chat's quiet, but I think that's just because I was kind of in a manic phase for the past few minutes. Anyway, let's keep going. Okay, so I apparently have this Barnsley transform function. Let me see what that was actually supposed to be doing to see if that was like literally the visualization that we want. So Barnsley transform modifies such that we perform the stem transformation, then the right and the left leaf transformations in successive leaves upward. Oh gosh, I don't know what I was doing here. Let me see. Okay, so we do have the Barnsley transforms in here. Do we have, here's Barnsley, we have them down there as well. So I think what I want to do is just create a function. I just want to create a function that's just like apply Barnsley. And it just like, you know, it has these functions that we apply in here. Just, I don't know, like somewhere else. Like it just makes this visualization a bit easier. We do know that at their heart, these are affine transformations, but that's okay. So here we're going to do, I think I just want to return back a vector. So I think if I just do vec, and then we do apply Barnsley. Also, I am, my C++ knowledge is, I always go back and forth between having a lot of C++ knowledge and having like no C++ knowledge. And I'm in the no C++ knowledge stage right now. So please forgive me. So here we're going to read in a vec, which is a point. And then we're going to read in an integer, which is going to be the function that we're going to be selecting from. So this will be, I guess I'll call it BID for Barnsley ID. It doesn't really matter so much. Go in here, up there. Okay. So if, I guess probably we want a case here. In fact, I think we can just grab this case in here. Yeah, I think that's exactly what we want to do. Let's just grab this case statement so we don't have to keep rewriting it up here. I don't know why I said it was T-type. Maybe transformation type. Okay, chotomate. Go over here. And let's just paste this guy right in here. All right, perfect. Let me remove some spaces, because who needs spaces in their life for X? Okay, and what we're going to do is say, instead of points of I, we're going to say point. In fact, we can just return. Yeah, let's modify this. So I think we can just return in here. So, well, no, let's do the following. Let's say point is going to be equal to that. There, and we're going to say point here. And let's just modify all of these points of I into point. Oh, it's so close to working as well. All right, so let's see if I can remember my regex or not. So because we're reading in vec point, I think we're going to have to return point down here. So we're just going to do return point with a semicolon, I think. And let's do set number, and let's just do some regex in here. So we're going to do, forgive me, this is going to suck, but I think I'm going to do 15 to 36 S. So we're searching through those. And then we're going to replace PTS of this with point, and then CG. Did that work? I guess. Yep. Perfect. I think it's working. Okay, so I think we did exactly what we need to do. Set no number. Oh, that was my Vim magic for the day. We'll just keep going. So let's go ahead and make sure the spacing is correct. So here we're just assigning all the points to be this. And what I'm going to do just to test this out is we're going to just switch the test case we have down here for Barnsley to just apply Barnsley. And then hopefully that is what we need to do. So here we're going to say PT is going to be equal to apply Barnsley of PT and 1. Probably 0, actually. Go here. Let's make sure it's actually spelled correctly, which it is not. It's still not spelled correctly. There we go. And now we're just going to do yank, and we're going to paste it down here. There'll be 2, 3, and 4. And then we should be able to DDDD. And in principle, if we change this to 1, 2, 3, 4, or sorry, 0, 1, 2, 3, we should have the same visualization we see up there in the corner, except now with our apply Barnsley function. So over here, I'm going to run the last G++ function, and hopefully this will work okay. Did not, because I'm stupid. That's okay. So we're going to change this to BID. Okay, try it one more time. And now we're going to run /a, Barnsley. And again, we're looking for the exact same visualization we see up there in the upper corner. So hopefully, when this is done, we get that visualization. And then we know that our function has worked and that we're good to go. Again, guys, if you have any questions, comments, concerns, just let me know, and I'll address it as soon as I see it in chat. I want to time this to see how long it takes for 20,000 points, because we could probably do with fewer points if we wanted to. I think we could do with, like, 10,000 points or something like this. We don't need anything crazy for this visualization right now. In fact, I'm almost positive we want way fewer points. Okay, let's take a look at the visual. And looks good to me. I'm happy with that. Okay. Yeah, I'm happy enough with that. Okay, so I think I'm going to do one more thing, which is I'm going to go over here. And we're going to move temp video.mp4 to just barnsley.mp4. Perfect. And what I'm going to do is I'm going to quit this over here, and I'm just going to mpv. What am I doing with my life? Projects, Simuleo, Sierpinski, Barnsley. 1 second. Fractal. Barnsley.mp4. Okay. That way, if we redo the visual, it doesn't, while we're remaking the video, it's not going to, like, destroy the, we're still going to be able to play it. Okay, so now let's modify our Barnsley transform in here, so it now uses apply Barnsley as well. I think, I actually don't know what the, oops, I forgot to loop that. Loop 0. Okay. I'm going to be honest in saying that I don't rightly know what this function is doing, and I probably should have, you know, in some ways, like, I don't know, documented what it was doing, but instead I just said to do, modify such that we perform a stem transformation, then the right and left leaf transformations, and then successive leaves upwards. So I'm going to run this function and see what it actually does. Yeah, so let's just go in here. So we have T-type. What is T-type? Oh, Barnsley transformation. What is this doing? Are we creating int n for i's I want to point size I++? Okay, I think actually what this is doing is I think it's doing exactly what we want it to do. I'm just an idiot. Okay, so let's go in here, and I'm going to say apply Barnsley point PTS of I is going to be equal to apply Barnsley of PTS of I T-type. Semicolon, and now we're just going to remove all this guy in here. And then in principle, this will work. No idea what working means in this case, but that's okay. So let's go here, remove this guy in there, add that there, write this, and now we're just going to run the last G++. Should compile, hopefully. Not that one. That one. It does not, because I misspelled Barnsley, I think. I did. Let's go up to the top. Barnes. There. XP. Try it one more time. Okay, so now we're going to run /Barnsley, and we're going to see what visual this gives us. Hopefully, it'll look pretty good. If not, that's okay. We can work with it. So I need to check to see what this visual is actually doing as well. So I'm just gonna look at the bottom of the screen and just like have an educated guess. So what I think this is doing is it's creating a distribution of random points, 1,000 of them, and then it's performing the third Barnsley transform. So I think what it's doing is applying, this is going to be the I don't know what transform this is. I'm just going to watch it and see what happens. Okay. So let's go here. Let's run mpv temp video.mp4. Starts with random distribution of points. Okay. Right. So now I understand my comment. So let's go up here. Let's modify this comment. Just for the record, guys, like, I did this years ago, like 3 or 4 years ago, and I never made a video on it. And the reason I never made a video on it is because I didn't have the affine transformation video. But now that we have the affine transformation video, it's like, screw it, let's just make the video. It should be relatively easy, hopefully. So what I want to do is take a look at each of these transforms separately, see what they actually do, and then see if we can piece together how that actually makes a fern in the end. So that's what we're going to do. So this does, this function creates a random distribution of points, and uses that distribution, uses the chosen transformation from the Barnsley Fern to get an idea what each one does. Okay, that should be fine. I'm still gonna leave the to-do statement in there because, yeah, who knows, maybe I'll do it one day. And let's just kind of, yeah, let's just do each visual and see what happens. So we just did 3, let's do 2 now. Write this, go over here, and I'm actually going to move temp video.mp4 into Barnsley 3.mp4. And then we just run it one more time. Again, guys, if you have any comments, questions, concerns, feel free to let me know, and I'll address it as soon as I see it in chat. Let me time this one just to see how long it takes. All these guys should take about the same amount of time, but this gives us an estimate for how long it takes to do everything from there. Well, if you want to be banned from stream, I can ban you. Let's do mpv temp video.mp4. So this is transform number 2. Okay, seems fine. Okay, so let's move that over here to 2. Now we're gonna do the same for the next transform. 1, and let's just run g++ and /Barnsley. I'm gonna be honest, I really wish Botuleos didn't say anything about Matlab. Like, that way I don't have to think about it. I just get really pissed off anytime I think about Matlab. But nowhere near as pissed off as I did during my PhD. Like, because I don't have to deal with it anymore. Like, I haven't touched MATLAB code in a long time, so I don't have to think about it. But man, yeah. That one just brings it up a bit. Okay. So, seems fine. Okay. So then the next one, Matlab, I highly doubt that. Matlab just pisses me off so much. Like, the thing about Matlab is it's fundamentally... Never mind. I'm not gonna go into Matlab rant. Truth is, I hate it. It's an awful language. It's not even a language. It's a glorified calculator. But like, fine. I understand that people use it. Whatever. Like, people make bad decisions in life. I can't help them. You know. Okay. Let's go here. Let's go here to 0. Write this. Go over here. Run the last move command to bring this to Barnsley 1. No, it's not though. Everything about MATLAB sucks. No, I'm just not, again, not going to talk about it. Look, you can have your opinion, totally fine. And I realize that, like, the people who only use MATLAB, it's just a predatory system. Like, everything about it is just, like, the worst thing in the world. Like, you couldn't make a worse language if you tried. Like, it's just so bad. But that's fine. A computer is a glorified calculator. In some sense, I'll agree with that. But my main reason why I say that specifically about MATLAB is that, like, I do have my opinion. Yeah, like, again, have your opinion. Thanks again for the cheer. Really appreciate it. My point is that, like, I'm gonna keep my blood pressure low, and, like, MATLAB, just everything about it just genuinely infuriates me to the point that, like, anytime, like, I had, like, one major fight with my girlfriend, like, ever, and that fight was nothing. It wasn't her fault at all. Like, it wasn't even a fight. I just got really, really angry because she just said the word MATLAB, and I just got just inexplicit. I just got really angry at that, just because I started thinking about all the things I hate about the language, and, like, just the thought about it just really pissed me off so much that I ended up just saying, screw it. I had to, like, leave the room. I got so angry. She said nothing but the fact that she used MATLAB, and I just got really angry. And, like, I realized it's completely nonsensical. Like, I should not have gotten that mad about it. Like, it's fine, but, like, I just couldn't. I just couldn't deal with it. Anyway, let's go here, run this, go over here, run g++, run /Barnsley, and then let's take a look at this last visualization. Okay, so then we're going to run, by the way, thanks again for the cheer. I'm sorry I'm being like really negative. I shouldn't be really negative. It's fine. It is a language that people use. I don't like it, but that's fine. Other people have their opinion, totally fine. But that's why I really don't like the fact that Bacaleo says Matlab is evil, because like every time they say that, it causes people to say, hey, I like Matlab, and then I just get really pissed off. When I shouldn't. I know I shouldn't, but I just like, just having Matlab in the chat just kind of like leads me to that. I was thinking about just banning the word Matlab from the chat entirely, just so no one says it. mpv temp video.mp4. Okay, and this one should just bring everything, yep, right to a stem at the center. Okay, so let's see if we can, yeah, let's see what we can do with this. So, yeah, okay, I now understand why I said what I said. Yeah, okay. I now understand. So here's what I'm going to do. I'm going to modify this function in here. Okay, let's move temp video.mp4 into Barnsley 0.mp4. Okay, then what I'm going to do is mpv Barnsley star.mp4. Okay, and this should give us, that gave us one video. I was expecting. Okay, well that's fine then, I guess. Why is this 10 seconds long? I guess it doesn't matter. Okay, and then stop moving. Thank you. What? Oh gosh, for Pete's sake, what is going on? All right, I'm gonna move that there. I'm gonna make it a little bit smaller. I don't know why this is having so much trouble with like just playing things. Okay, so I'm gonna play this. So what I'm trying to show here is the 4 different transforms for the Barnsley Fern. The first is a transform for the stem. Very clearly, it makes a stem. It takes a random distribution of points and moves it into a stem. The next transform I'm going to show is a transform that creates successive leaves going upwards. It should be done now. Okay. So here we see that it basically just moves whatever we have, moves it upwards. The next one should be a transform that will allow us to take, what does this one do? This one should, it should flip, I think. How does this one make sense? Okay, I don't know how that one works exactly. Let me see the last one. I feel like the Barnsley Fern in particular must start at like 0, 0 for some reason. I feel like if you start the Barnsley Fern at a random point, I feel like it, yeah, I don't know. I feel like it does something weird. Let me check to see, let's check to see the visualization that I have. I've been gone a while. Are you still in Japan? I'm not in Japan. I've actually been in the US for the past year and a half. It's been a bit of a story, honestly. So I basically moved to MIT to work there for, at December 2019, I started working at MIT. And I ended up, again, just deciding against continuing at MIT. This doesn't mean I'm going to stop doing research. I still very much enjoy doing research. But what it does mean is that I felt like the research I was doing at MIT was not leading me down a path that I felt was fruitful. In the same way that I felt like the PhD wasn't leading me down a path that I felt was fruitful. You know, so like I ended up like at the end of the PhD, you know, doing a lot of computational physics. And though I really liked the computation, I didn't very much like the physics. So my hope was that by the time I go to the MIT position, that I would focus way more on the computation and way less on the physics. But that just wasn't what happened. It ended up being that for the computation, I wasn't really doing computation. I was basically doing tech support, which is again what I was doing during the PhD. And it turned out that I was still doing a lot of physics. So it was kind of like you take the PhD and just add a bunch more stress to it. And you still don't get to do what you want. So I was like, okay, let's, you know, I do recognize that like I'm in a very privileged position here and that like I probably should be keeping this position and all this kind of stuff, but I kind of just decided against it. So this year, what I'm actually doing is I'm working with Grant Sanderson with 3 Blue and Brown on some stuff on the side. And I'm focusing my efforts on basically just making my own content as good as it can be. And this means doing some independent research here and there. And what I'm currently focusing on is a bit of fractal compression. I don't expect to actually like, you know, break through the boundary of human knowledge with this particular topic. But what I am hoping is that we get to that boundary. and we can show people how to get there, and then slowly but surely start to etch out my own unique interest, my own unique research interests, kind of, in an open and in an open way that people aren't used to seeing. So that's kind of where I'm hoping to go with this. Also, Peace and Life, I swear I've seen you within the past year, so I feel like it hasn't been that long. Anyway, I am sorry for the weird biography in the middle of stream there, but that's kind of where I'm at right now. I am in Boston. I will be in Boston until the end of May. That's also fair. Again, I don't give everyone my biography. It's kind of a weird thing to do. But I'm in Boston right now. I will be in Boston at least until the end of May, where I'll be moving back to Alabama for 2 weeks, and then I'll be going back to Okinawa. And then after I'm done with Okinawa, I'm then going to be moving to Barcelona. So in the next 3 months, I'm going to be going to Alabama, then Okinawa, then Barcelona, and I'm going to be staying in Barcelona for a few years. The reason I'm saying that on stream is because that means that at the end of this month, I'm going to have a week off. And then I'm going to have 2 weeks off where I have to quarantine in Tokyo. And then I'm going to have 2 weeks off in September where I have to quarantine in Barcelona. So, Ramo, thank you so much for following. Really appreciate it. And also, to be fair, I'm working on my postdoc too, moving to Frankfurt. I feel like that's a common case. I don't know how to put this, but I feel like academia is one of those things that, I want to love it so much, I love the idea of research. In fact, I love doing research. I love reading research papers. I love, all this kind of stuff. But also, it can be quite brutal, for a different postdoc. That's fair. I mean, I'm not going to ask the reasons why you left the postdoc, but we'll see. Barcelona's nice. Got to see La Sagrada Familia. I can't do any Spanish, so I need to learn Spanish. That's one thing I need to do. In particular, I need to learn Catalan, Cantonese. No, that's different. Catalan's a language. I'm sorry, I suck. I'm so bad. But no, we're gonna see how that goes. It's gonna be an interesting move. Park Güell is amazing too. I need to learn way more about European culture and stuff. But what I am saying is that stream times will be changing a lot in the next few months. And so I don't know. I've been kind of 50-50 on whether I should be doing a lot of streaming or a little streaming. I don't know. I'm kind of all over the place because I know that stream times are going to change and all that kind of stuff. Food. I'm a bit worried about the food because I feel like it's a lot of seafood, and I'm vegetarian, not pescatarian, vegetarian. So I don't eat any meat or anything. So I don't know. I kind of feel I'm a bit afraid that the food might be hard to find. Gaudi is a genius. The Escher of architecture. Totally fair. I mean, it's stuff that I don't know. Okay. So we have the 4 transformations. What I'm trying to do is figure out how those 4 transformations come together to create this fern. Oh, hello. This fern, right? Because in the end, those 4 put together will create this fern. Hello, the Henry Stickmin roleplay server I joined the other day is inactive right now because most of the members are at school or work in the same range of time zones, so there went my morning. Sorry about that. I'll pop in later. Toodles. See you, peace. I'm only able to stream for 2 hours today, so I will actually have to go at 6:30 Eastern time. So sorry about that. But I'll be back tomorrow for a bit, for a longer stream. I feel like Bacheleo is code specifically to respond to my messages at this point. I don't think so. I mean, it just responds a lot, and it just happens to be, I mean, clearly it's not, but it just happens to say things a lot. So, okay, so we do have the 4 transforms, and my question is, how do those 4 transforms create this fern? And so what I'm going to do is I'm going to actually take a look at our Barnsley function in here, and note that I started the Barnsley Fern at a very particular point, 0, 0. So what I want to do is modify this so that we start at a different point. So let's change our initial point here to be some random point, and I'm just going to do rand. And let me see if this also creates our Barnsley Fern or not. It's probably going to be a really messy Barnsley Fern, and I just want to see what the differences are. So let's go down here. I'm going to run just the Barnsley function in here. Run this, go over here, and just run g++, and give it a go. Rand. Conversion from int to double. Oh, correct. What I need to do is, my bad, pt equals, I need to do rand modulo 100 divided by 100 divided by 100, and I need to do that for this as well. Okay, try that. Oh, Okay, so that's still saying it's an integer. So if we divide this by 100.0, hopefully that'll do it. Okay, that seemed to work. So now we're going to run /Barnsley and see what we get. It's going to take just a second to render, so. So because we're leaving this particular place in May, at the end of May, we have a lot of people that are like coming through the apartment just to see it. You know, a lot of like the realtor is bringing people by just to see if they want to buy the place. And like, I do understand it. It's fine that they're doing that. But it just means that like, I'm having trouble finding streaming times because every time I'm like, oh, I'm going to do a stream now. Like they're like, oh, you know what? We're going to invite someone over at like 4:00 p.m., which is like directly in the middle of when you were going to be doing the stream or something like that. So there might be a day in the near future where I just say, you know, screw it. We're just going to stream anyway. And there's just going to be like a 15-minute break whenever these people walk through. And I'm just going to like show the Simulatus is doing something embarrassing screen or something like that. Okay, let me run MPV. Temp video.mp4. Okay, this is still fine. I'm not seeing a problem with it. So let me try this again. What I'm gonna do is I'm going to use fewer points. So let's change this to let's do 1,000 points, and I'm gonna start with 0.00. And we're going to see if we can still draw the fern pattern with that. So it should be in here. And the reason I'm doing this is I essentially want to see a low quality Barnsley Fern with fewer points. And then what I want to do is start with a random point and see if, you know, how messy the fern is. I know that the fern is the attractor to the system, but my question is, how attractive is it? Like, and I don't really have a good, you know, way to judge that. So let's run this, write this, go over here, G++. /Barnsley. It should be a lot faster this time because we have way fewer points. And then after that, we're just going to run mpv temp video.mp4. So that is a very low quality fern, and that is okay. That's what we're looking for. So let me move temp video.mp4 into Barnsley lq.mp4. And now what we're going to do is we're going to run it with a random point. And again, I just want to see what the difference is. I don't know. There's some stuff. I remembered some context I should explain to you about my life. Fair enough. Please do. All right, let's go here. Write that, go here, G++, and run /Barnsley. And we're just going to see what the difference is between the two of them. So we're going to run MPV. When it's done, give me a second. MPV temp video.mp4. Okay, so here is exactly what happened. I see. Okay, let me move this up here. Oh, this is going to be a bit messy, ain't it? Okay, and now I'm going to run quit MPV temp. I'm sorry, Barnsley low quality.mp4. Okay. Oh no, that's not what happened. Okay, well then I'm not really sure. So looking at the difference between these ferns. Sorry, like honestly, my gotta love X11. Okay, give me a second. I'm struggling a bit. Okay, I am struggling to find the difference between these ferns, if I'm being honest. I mean, we do know that the fern is the attractor to the system, so we know it's supposed to look like a fern in the end. I've recently taken up a quest to collect as many cringe fandoms as possible, so that I can become maximum cringe. That's a very interesting quest. Okay, so why is it slow when I move over that region of the screen, but it's fine elsewhere? Is there something wrong with that region? I don't know. Anyway, again, I'm not really seeing that much of a difference. What I would say is that we have a crisper point on the fern over on this one than we do up here, but I don't know if that's. Let me run one more set here. Yeah, let me run it one more time. We want a random number, but this time I'm gonna do like more of a, 4 is a pretty random number type of thing. So let's see, what do we have here? Up here, I'm going to actually give it a specific location of 0.5, 0.5. Actually, no. Let me give it a specific location of 10, 10. 10, 10. And let's just see what happens with this one. Yeah, 10, 10. 1 second. Here, there, right that. Over here, we're going to run G++. And then want to move temp video.mp4 into... 1 second, I have to think about this. Barnsley LQ rnd.mp4. All right, perfect. Now we're going to run /Barnsley, and I'm just going to see if there's a difference between... I think it's fine that they're integers. I think. We'll see what happens. So let me do mpv temp video.mp4. Yeah, it was fine that they were integers. Okay, interesting. So I'm looking at the very tip of this fern, and I'm now going to compare that to the tip of the next fern, which is going to be mpv Barnsley low quality random. Okay, the tip here is quite different, and you'll note that we have like some sort of weird structure going on in there. Okay, so now the next one I want to do is just Barnsley low quality. It is quite difficult to tell the difference. So let me just run this a bit longer. So we're going to run maybe 10 times as many points. How about 74? Yeah, we can do 9974. Should be fine. R9974. Perfect. Over here, let's run G++. And this is going to be a slightly higher quality version of that fern. Marks 33AZ. Thank you so much for following. Really appreciate it. So let's run /Barnsley. It'll take just a second longer. I don't remember. It won't take too long, like maybe 30 seconds or so. And then I'm just going to take a look at the quality of that one and see what happens. I mean, you know, we know the fern is the attractor to the system, so we know we're going to get a fern at the end. I'm just trying to figure out, like, if there's really that much of a difference. So, mpv temp video.mp4. Okay, so here we see we have a point starting over here, a point going over here. My assumption is that this over here must be... I don't know what that is. Oh, okay. So we must have... We started like 97, 94, so we must have been way up here in the upper corner. And then like somehow it flipped over and over and over, and then eventually it landed itself over here on the stem. And then when it got on the stem, it then created this other structure. Okay, perfect. So that is exactly why I left myself the comment up here as a to-do statement to modify this function such that we perform the stem transformation first, then the right and left leaf transformations, and then successive leaves upwards. That's why I did it, so that hopefully that would generate a fern-like pattern without as much randomness. So, you know, 3-year-old me actually remembered something, or me from 3 years ago. Okay. So here we have the update function. I feel like what I actually want to do here is, how do I want to do this? So we have the random function generated. We are applying the transformation to the random points. I feel like what I want to do is create a new function. That will start with basically this bit in here where we create the random points. And then basically perform this operation. Basically perform this operation with the apply Barnsley of points of t-type and all this kind of stuff. And just it iterates through. So essentially, I'm just going to recreate this function. I realize, I'm duplicating some code, but screw it. So that'll be this function in here. So it's going to be void Barnsley. I'm going to call it quad transform. And it's going to read in basically the same operations here, there. And let's just copy some code. I'm sorry, guys. So in here, we're going to grab that. Chotomate up here, paste that. And then I essentially just want another for loop outside of this guy in here. So it's going to say for j, chotomate, int j is equal to 0, j is less than 4, plus j. 1 second. If you couldn't tell, I suck. Let's go in here, paste that there, add some spaces. Okay, so now what we want to do is apply t-type, but it's not t-type. In this case, it's going to be j. And this, I think, should do it, as long as we keep track of the timing here. So here's going from 60 to 120, and what I want it to be is something else. Cool, pre-increment. Thanks. People got really mad when I was doing post-incrementing, like a long time ago on stream. I don't remember why, but like there was this huge debate between pre-incrementing and post-incrementing, and I was like, screw it. You know, as a meme, we're gonna do pre-increment, and then all of a sudden, everything now is pre-increment for C++, even for loops, when pre-increment doesn't matter. And if for those of you guys wondering why pre-increment and post-increment matter, it's because in C++, if you say I is equal to, I don't know, 1 plus plus, I will be equal to 1, because it's going to do the plus plus operation after the assignment operation. So you could run into situations where like you do the assignment at a place when you don't want to. So usually, you know, you want to make sure you do pre-increment in this case. So you'll do, you know, plus plus 1. So I is equal to 2 in that case. I think the compiler nowadays like fixes it so it doesn't matter, but there was a time when that was the case. I plus 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 is undefined. I didn't know that. Cool. Okay. So here what I'm going to do is it's going to be 60 plus 60 plus j times 60, and then the next line will be okay, that's one way to do it. 120 plus j times 60. All right, perfect. Let's see how we go from there. So let's do that, write that. I don't know, let's run it. What's the worst that could happen, right? 1 second. Quad changes to that. All right, let's just run it. G. All right, Barnsley. I don't know what's gonna happen. Let me get some water. Actually, I think I did this in the wrong order. The worst that could probably happen is segfault data corruption. I don't think you understand. I have literally set my computer on fire before. The worst that could happen is my computer is set on fire again. Okay, let's do mpv temp temp video.mp4. So it should be the stem operation moving upwards over right. So that's not the right order. Let's try this again. So we're gonna do the stem operation first, and then let's see. So I want to modify the order in which we go here. So what I'm actually going to do is the following. I'm going to say, this is the wrong line. Up here, Barnsley quad transform. We have the 2 for loops in here. So what I'm going to say is std vector of int. Screw it. I don't need this. I can just do the following. Order is going to be equal to int star order is going to be equal to 0 2 3 4 1 I don't think that's going to work, but at the same time we're going to see order of j, and I don't think I use j anywhere else. Oh, I do there, but that's fine. I actually want it there. Okay, that's going to break. I don't remember what the actual notation is, but yeah, I knew that was going to break. How do I define an array in C++? Define array C. Do I need the squirrely brackets? Is that what I need? That's what I need. Yeah, okay. So I need to do order here is equal to that, I think. No! Ah, I thought it was right. Const char image. C arrays. Tutorial point. Let's go. Lose the star. Oh, really? Wait, now I'm confused. So should I put a 4 in here? That's Barnsley. And see what we do. What we got there. Yeah, that must be it. I'm sorry. My C++ knowledge is pretty bad. Again, I used to code exclusively in C++. It's been so long. Okay, let's see what happens. I'm going to do mpv temp video.mp4. So we start with the stem operation, then we should go over a bit. Oh no. That didn't do anything. Right. So, this is a bit more complicated than I thought it was going to be. So we do have the transformations. But I'm not actually sure how those transformations create the Barnsley Fern. It did something. No, you're right. It did something. Okay. I'm gonna watch it one more time. So again, we combine all the points into the stem. Okay. Let's just watch the transforms again. So we're gonna do MPV. MPV Barnsley 0.mp4. So this is the transformation that brings them all into the stem. That is chosen 1% of the time. Okay? This is a transform that creates successive leaves upwards, I think. See how it goes up and a little bit to the right. Okay? So the next transform is going to be, give it a second, this transform, I don't know what this transform does. I'm going to have to Google that one. I think this one takes wherever we're at and it moves it to the... Okay, I think this is what this transform does. I think this transform will take this region of the leaf, kind of, and rotate it over to be on like the top end of the leaf in there. So that's why this side looks exactly like this side of a leaf. And then I think the last one will flip it over so it can show the other side of the leaf as well. So I think if we look at that last transform, here, 3, it should, yeah, so it flips it around, and my assumption is, actually, why does it flip it that way? Okay, let me just read Wikipedia, see what they say about each of the transforms, and now we're going to try to make it like, yeah, we're going to try to make it like way more visual. That's definitely activities I see on my screen. That's a remarkably smart procedural generation algorithm that rotates out the leaves. Right. So let's just take a look at the Barnsley Fern again, and let's see what they have here. So that one makes the right side mirror the left side. Yeah, but yeah, I mean, let me think. Okay. So this coordinate transform is chosen 1% of the time and just maps any point to a point in the first line segment of the base of the stem. Yep, exactly what that does. We showed that in the animation. Perfectly fine. Okay. This coordinate transformation is chosen 85% of the time and maps any point inside the leaflet represented by the red triangle to a point inside the opposite smaller leaflet represented in the blue triangle. So this is where I get confused. How does this transform, which is just an affine transform that we saw before, how does it know that we're grabbing this particular red region to transform into the blue region? This coordinate transform is chosen 85% of the time and maps any point inside the leaflet represented by the red triangle to the point inside the opposite smaller leaflet represented by the blue triangle in the figure. Yeah, how does it know how does it know to grab this triangle and move it over there? So what that says to me is that somehow all of the other transformations will only create points somehow create points in that triangle. And I don't understand that. So then the third one says this coordinate transform is chosen 7% of the time and maps any point inside the leaflet represented by the blue triangle to a point inside the alternating corresponding triangle across the stem. It says across the stem, so this one must go over this way, which is fine. I don't mind that one too much. And then the last one is this coordinate transformation is chosen 7% of the time and maps any point inside the leaflet represented by the blue triangle on to a point inside the alternating corresponding triangle across the stem without flipping it. Wait a minute. All right, give me a second. I assume it knows because the transform is defined in such a way that rotates and shrinks the image so that the red triangle moves to the blue location. Well, right, no, but right. So the thing is, we're not transforming a group of points, right? We're transforming one point, right? And so if 85% of the time, yeah, that's the thing that gets me. So we have a single point that's up here, right? So we then move it over here to this blue triangle, right? But then we have an 85% chance to choose that same function again. So what's going to happen then? It rotates here again? Like, yeah, my observation is that attractors can be understood as transforming groups of points, though. Yeah, that's the thing. I don't think it can be understood by groups of points in this stage. But the point is chosen by the coefficients of x and y. Point is chosen by the coefficients of x and y. Well, right. Yeah, that's true. That was the point I was trying to make before. Did I put these in that order? I feel like maybe I didn't put them in this order in my code. But let me try to make a differentiation between F3 and F4. So this coordinate transform is chosen 7% of the time and maps any point inside the leaflet or penna represented by the blue triangle to a point inside the alternating corresponding triangle across the stem. Okay, hey BTC Fly. So this coordinate transform is chosen 7% of the time and maps any point inside the leaflet or penna represented by the blue triangle. Are these not the same statement? These are literally the same. Yep. Yeah, they said the same statement, and then they said it flips it, and without flipping it. It's like, well, that doesn't help. You didn't miss too much, BTC Fly. We were just kind of hopping into the Barnsley Fern today. Reason being that we want to kind of look at other attractors that are not just the Sierpinski triangle, because I do want to test that paper out that we had yesterday. Because if we looked at it, the paper had a very particular case, which was the kind of Sierpinski triangle-esque visual, and I was like, you know what? Let's just try something that's not Sierpinski triangle, and see if that also works. By the way, BTC Fly, thanks for the links on Discord. I was kind of looking at those this morning as well, but I kind of ran out of time. Was working on some stuff for Grant this morning. Okay, so anyway, my point is that, like, the reason I don't like the Barnsley Fern is that no matter how much I look at it, it's still magic. And I hate that. Like, it's still like, you know, I'm not saying I am saying I don't like magic. Like, the reason I don't like, for example, space is because it's always treated like it's magic. You know, like, people are like, oh, here's a supernova, here's a black hole. I'm like, well, great, man, but like, can you, like, give me something more than this is a supernova, you know? Dre's paper has a lot of creative choices, like, involving 1 over r squared. Right. So this is why, like, I really do feel we need to, like, broaden beyond Sierpinski's triangle. Like, we need to do things that are just, like, more complicated, right? To rephrase my argument, transforming a randomly chosen point can be understood as transforming the range of starting points. Right, so that's exactly why we did this visual in here. So if we go over here and we run mpv temp .video.mp4. So I tried, yeah. So I tried to do that, right? So I tried to say that, you know, we start with a random distribution, and if we apply function 1, they're all going to be this guy. So what I'm going to try is kind of maybe a different, yeah. So we apply function 1, then function 2, and 3, 4, whatever. We apply the 4 functions in a particular way. And we do notice that they all kind of, like, come together. Oh, right. So, I'm sorry. We could do a Menger sponge, right? But I want to do something that was, like, kind of a different type of attractor. Supernova do have a physical explanation. Okay. I said a bunch of things, and I didn't really qualify any of those things. So let me go back over here, and let me just talk about that. Journal, new page 4. 1. Next up. Why is the next up the Barnsley Fern? That's the question. The reason the next up is the next attractor up was the Barnsley Fern is that it works fundamentally differently than the Sierpinski triangle. Well, it's still a bunch of affine transformations, but it's not like it's not like f plus 1 over 2 type of thing, f plus a over 2 or something like that. Some nonlinear things involving, right. So what BTC over here is saying is kind of what I'm getting at. Like, we wanted to do something that wasn't like kind of like P plus A over 2, and like the Menger sponge stuff like this is kind of in the same ballpark. We could have also done instead of the Sierpinski triangle, we could have done or the Barnsley Fern, we could have done like restricted chaos games and stuff like that, which I think the Menger sponge falls into. But we just kind of, I felt like going this way, you know. I have WebGL implementation of Electric Sheep on my GitHub, works in browser using WebGL. Right, yeah, I like, wait a minute, what is Electric Sheep? I didn't, is that a, yeah, okay. That is exactly what I thought it was. I didn't realize shaders could do that. Yeah, I did, like, I mean, don't get me wrong. I mean, obviously shaders can do that, but I thought that you'd run into issues with the computation there because, yeah, I understand that the Electric Sheep is the iterative function system and genetic algorithm thing, but my point was that, yeah, you can link it, but my point was that, like, doing this on the GPU kind of sucks because, like, iterative function systems on GPUs kind of suck. So I was surprised that you could do it relatively fast enough that it would work with WebGL, you know? I mean, I'm interested to see if it's in real time, because if it's in real time, then I'm actually quite interested in it. Okay, so then the other thing I mentioned was that, all right, 2, I don't like space and stuff, because it's all magic, right? And what I meant there was that, so I used to actually do research in supernova remnant plasmas, right? That was my original, like when I started as an undergraduate researcher, I did a little bit of research into pain tolerance in suicidal patients, and then I kind of jumped into supernova remnant plasmas. A lot of plasma research is what I did at the time. The reason I'm always kind of put off of space is not because of the research in that area. I actually really enjoy the research in the area. The reason I'm put off of space is that the way it's taught in popular science is incredibly, like, it's always taught as this thing you should be astonished by, and they kind of hide the actual interesting bits, right? So it turns into something, like, the way it's taught in school is always taught as, you know, this thing you should be in awe of, like, oh man, we went to space, oh, we went to the moon, oh man, there's so much more out there that we could explore, and all this kind of stuff is very unappealing to me, because it feels like just something people are giving you because they're like, oh, this is going to be cool. It's like when people show you a magic trick, it's like, oh, this is going to be cool. I'm going to show you this thing that's going to, you know, put the wool over your eyes or whatever, and it's going to look like this woman is being sawed in half. I'm like, who cares? Like, I don't care about a woman being sawed in half. I'm interested in the trick that allows for that to happen. But the actual, like, thing, the woman being sawed in half, is super boring. Like, who cares? Like, the only, like, the interesting part is learning how it's done, right? And so, for me, specifically with space and space exploration and stuff, it's always taught in this way that's just kind of like, I don't know. I don't like it that much. It's always taught in this way that's just kind of a bit too, like, I remember I was talking to an astrophysicist one day, and they were like, they told me, like, oh, I knew I wanted to be an astrophysicist the moment I looked up at the sky and I saw there was so much out there that I wanted to study. I was like, oh, okay, like, cool. I didn't think any of that. I also don't care, you know, like, I was interested in physics the moment I realized there was more to it than just a starry night sky. Like, I was interested in physics the moment I could code something up and I could be like, hey, this is actually really cool. Like, the moment I saw the math and I was like, this is how it works, I'm like, that's great. Like, that's the type of stuff that I like. So that was my point there. My point wasn't that, oh, you know, space is boring. I'm just saying that, like, the way it's taught is typically in this weird way that I think is not conducive to learning, at least not for me. Okay, let me catch up on chat. If you use GPU to transform the points and render using GL points, my Vulkan implementation is very fast, real time, but of course, if you have low density, you get noise. Yeah, feel free to link it. I was actually interested in seeing seeing how long it takes to run, which leads to density estimation, right? No, I'm very familiar with the fractal flame method. I would research plasma tolerance in supernova patients. I mean, fair enough. I don't care about women being sawed in half. Mathematical deep space exploration requires less rocket fuel and manpower. Yeah, so Yeah, I mean, I guess because it's just theoretical. I see. I didn't mean to be rude. Sorry. I understand your point of view. Also, I do apologize. Like for some reason, every time I say something, like sometimes people think that I'm being like very frustrated or angry about this thing. I'm not frustrated or angry about this at all. Like I generally just wanted to like get my point known. That like I just feel like this. I don't know. I would much rather just be given a research paper as a kid. Like if I was literally given a research paper on astrophysics, I think I would have enjoyed astrophysics. But I wasn't. I was given like all of this like random gobbledygook, and I was like, I don't like it. I don't like this like weird magic trick that you're trying to put over. Like you're trying to make me interested in it, and in that process of trying to make me interested in it, I'm not interested in it. But if you just gave me a research paper, it's like, hey, this is on the boundary of human knowledge, I would have been like, boundary of human knowledge. I'm sure I'm smart enough to figure that out, and I would have spent hours trying to figure it out because I enjoy that process of being like, you know what, at the time of publication, this paper was something that pushed the boundary of human knowledge forward. It was something that no one had ever done before. And giving me a paper and saying, hey, this was new in 1960s, I would have been like super cool. I would have been so into it. I know because that was that's the reason I got into neuroscience, actually. I got really into that type of thing because it was new, and it was like there was a sentence in there that really got me. Like every time I was reading papers on neuroscience and neurophysics and stuff was what I was really into at the time. Like there were all of these people that would say, this particular topic is, still under discussion or still under debate, or people are still looking into this thing. And I got really into it because I was like, man, I love this idea that people don't know about this one thing. And I love trying to learn more about that thing. So basically saying that space is taught in a way that discourages trying to think about it. Right, exactly. Let me take a look at this. Yeah, I'm interested to see how fast it runs. There, L. Okay. Can I just... Oh, I'm going to have to... Oh, try it here. Perfect. Okay. Yeah, this is about the speed that I was expecting. Yep, perfect. So if we... Yeah, that's what I was expecting. So we can... What's position do? Color? Okay. I screwed it up. But no, that's exactly what I was expecting. Yep. It takes about a second or two to render the entire image. I just removed it, and I didn't mean to. Take a look again. Can you change the flame? Okay, so that's the gamma factor. Yeah. Okay, cool. That's what I expected. Thanks for that, by the way. Yep, that's a good link to look at. Move this over here, so I have it saved. I've gone further with it, not open source yet, but my Vulkan implementation takes much less time. Yeah, that's the thing. Like, I know for a fact that iterated function systems are just really bad on GPUs, just because they're iterated, and how do you speed that up and all this kind of stuff. I didn't realize. I mean, I guess Vulkan Compute can probably do it much better because you have like a much better grasp on what the GPU is doing with Vulkan. But I'm surprised you could do so fast with OpenGL, honestly. So my Vulkan implementation change flame requires changing shader. Right. I've had a similar experience with linguistics. Language is a beautiful blossom of diverse rules and cultures across the planet. What else is new? It's against the rules to say a big red balloon. Now I'm curious. Right. Yeah, I totally understand where you're getting at. I'm doing it with compute. Exactly. Yeah. So if you use Vulkan Compute, I can imagine that because I think Vulkan Compute gives you the same, basically the same tools that you're used to using if you're using like maybe CUDA or OpenCL or something like that. And I guess you get most of the tools with OpenGL that you get with OpenCL. But I always feel like specifically if you're trying to use like shared memory and stuff like that, it's actually kind of a bit slow if you're going to do that in OpenGL, I feel. You read it wrong. A big red balloon is fine. A red big balloon. Sorry. But yeah, I know what you mean. Hey, Reem, how are you? Okay. So, right. So what I'm trying to do now, I don't have to... Oh, no. I've got about another 45 minutes or so I can stream. I really do have to go at 5:25, so maybe an hour. Sorry, 6:25, so maybe an hour from now. In 40, you can start playing with quaternionic functions. Yeah, I knew exactly what you were getting at with the adjective order, right? Like, as English speakers, we tend to put things in a particular order, and like, we don't think about it. It's just something we do. And so for non-native speakers, like sometimes they're going to say something that is not in this order. Like again, big red balloon versus red big balloon. And it's kind of weird why we're in that order and stuff like that. I think I remember you talking about that a few years ago, honestly, Gibbous. Death Eater, how are you? I'm not going to do the push-ups today because I don't have so much time to stream. But tomorrow, definitely. Instead of an iterative function system on 2D, I'm doing it in 3D, and I have a resolve with sorts of points depth. Right. Big red balloon, red big balloon. Per pixel, linked list. Right. I'm interested to see why you used a linked list, though. So the big red balloon sounds correct. Red big balloon sounds incorrect. Technically, they're both correctly. They're both fine. But, you know, one of them misses the adjective order, which is what Gibbous listed before. Yeah, exactly. So, order independent transparency. Okay, I see what you're saying, right? Because you could have different functions. Yep, I see why you need that. Technically, red big is still wrong. Well, okay, but adjective order is not something that you have to follow. It's something that's expected to be followed, right? I mean, like, this is... Adjective is a word... okay. Sorry, must have been right down here. In many languages, attributive adjectives usually occur in specific order. In general, the adjective order in English can be summarized as opinion, size, age, shape, color, origin, material, purpose. Yeah. But I thought it was like still your choice if you didn't want to use it. It's just that like it's going to sound really wrong. It's not either of those things you described. It's something that English speakers follow but reflects almost unanimously. More like a law of physics than a law of justice. Right. That's exactly what I was saying. Like it's not it's something that you're just doing. By the way, PJZ here, thank you so much for following, really appreciate it. But is that specific to English? Well, no, it's not specific to English. Other languages have it as well. But specifically for English, that's what this is. Let's see. Yeah. But yeah, so like Ibis was saying, it's just something that like people do naturally. You can hold an apple up above the ground, but that doesn't render gravity optional. Well, I mean, I don't think this is like a law, like a gravitational law. Like, because people definitely break this law, like, all the time. You know, if people don't know, like, if they're non-native English speakers, I mean, like, my girlfriend, for example, has multiple times broken this, you know, in talking to me. And it's just, you kind of, it can't be a law, like a physical law, if people break it when they're non-native speakers, right? Like, that would be saying, like, someone coming from Mars wouldn't, you know, follow the same gravitational constant that we do when they go to Earth. So I don't know. I do agree with you in saying that, like, it's a bit like it somehow is more fundamental than any of the laws that we have, you know. Deviant a bit, thank you so much for following, really appreciate it. Another fun linguistics English rule I learned about recently. Yeah, go ahead, talk about it. Okay, so what I'm going to do is take some time looking back at the Barnsley Fern and trying to figure out what these transforms do. We already know what they do, but I'm going to try to like find a visual for it that works a bit better than what we currently have. So, yeah, that's what I'm going to try to do. So, like, okay, we know that the first transform, you know, brings all the points to the stem. Totally fine, not a big deal. So the next question that I have is what happens if we... Okay, we could just follow all the points in space and just watch them as they do their thing. That would be fine. I'm now trying to figure out how to do this visual. When you repeat the same word with a different vowel for effect, the vowels follow the pattern I-A-O. Might help to reverse each transform before applying the next as part of the demo. Well, we don't necessarily have to do that because we have the visuals for each one of them individually, right? So we could do Barnsley 3, which is just a random distribution for the third transform. And then we have Barnsley 2. You know, like, I have the random distribution of points doing the transform every time. It's just I'm kind of struggling here to, you know, for example, here, let me do Barnsley 1 here. Okay, so Barnsley 1 is the one that's chosen 85% of the time. And what this one's supposed to do, here's your random distribution of points. So this transform in here takes, why is it so slow? It's supposed to take this red region in here and transform it to the blue region over here. But when you run it, it kind of just makes it go up into the right a bit. And so the question is, Why? How does this bring it over there? There are visualizations for the complex number in Matlab following the point as the branches of the tree of probabilities would be interesting. Right. Flim flam, ping pong. Oh, I see what you're saying. Okay. TikTok, crisscross. Yeah, fair enough. No one would say flam flim or pong ping. I think you're mixing up the order of the transforms. I don't think I am. In fact, I'm almost positive I'm not, but I can take a look. Let's go over here. Let's go there. I'm just going to open up a new browser. 1 second. And go into Barnsley Fern here. There. And let's just check to make sure. So I'm going to go up here to the top. And so we have 1, 2, 3, 4. So this is the stem operation. So we had that one fine. This one right here is 0.84. Oh, why is it 8.4? Shouldn't it be 8.5? Okay, well, there was a small variation, but 8.4, 8.5 isn't going to change anything. Let's go here, 2, 5. And we're going to change that to a 5 as well. Now it's right. The triangle one is transform 2. I think that was the triangle I was looking at. Yeah, I was looking at transform 2. So we're off by 1 because it's case 0. I was looking at this one. Right, which is case 1, which is this one. So it is this one. So like, you know, it is definitely the right one. So let's see. So then case 2, we have point x times 2. I'm just making sure that we have the right numbers and everything. Everything else seems fine. I mean, I had 8.4 instead of 8.5. I'm not exactly sure why I had 8.4 instead of 8.5. Must have been like a typo a long time ago. But it doesn't really change too much of the structure, honestly. So let's see. I'm just making sure the other two are also in order. 2, 2, 6, 2, 3. Yep. So this order in here, F1, 2, 3, 4, is the same order that we have in here. It's just we're off by 1 because I'm in C. So case 0 is the first case, or is case 2. So the triangles illustrate transforms 2 through 4 in different ways according to their respective descriptions. The triangles represent 2 through... Yeah, that is correct. Right. So if we look at the visualization here, it says down here for F2, which is F1 in our case, this coordinate transformation is chosen 85% of the time and maps any point inside the leaflet represented by the red triangle to a point inside the opposite smaller leaflet represented by the blue triangle in the figure. So maybe I'm misreading what that's saying. So it is saying the leaflet represented by the red triangle, so it's taking any point in the red triangle to a point inside the opposite smaller leaflet represented by the blue triangle in the figure. But in general, that's not exactly what we're seeing. We're seeing that it's actually just moving it consecutively up. So let's go here. Sierpinski is a nice example because you can just think of it as if you're picking the halfway point from the current point to the random triangle. Right, exactly. That's why we were focusing on Sierpinski for a while. So 2 is a shrink, 3 is a flip, and 4 is a rotate. Right. That's what we're seeing as well. So if we go here, so we do 2. So this should be a rotate. I'm actually not sure which one that's corresponding to. And then this should be a flip. Okay. So what we see is we have the stem operation. So we have the stem operation, which is this one here. Barnsley not. So this one just brings all the points, bring them to the center. Then we have another operation, which will create basically successively smaller leaflets as you... sorry, wrong one. Which will create successively smaller leaflets as you go up. So we should create, up. And then the next one will just be kind of up and shrink as you go further and further up towards the top of the triangle. And then the next one we want to do is 2. So this one I'm having trouble with. It clearly creates like a smaller structure. So yeah, instead of throwing the affine terminology, yeah, the thing is, I think the affine terminology actually helps a bit. Actually a lot, honestly. And since F1 is a strict attractor, I think I made up, the other transforms can be understood as transforming the stem. So I thought that as well. That's why I did this in particular the order I did it before. So for example, if we do mpv temp video.mp4, I started with the stem transformation, because I thought, oh, maybe it is just a transform on the stem. And then I moved up and around, and it didn't really do what I was expecting. But let me watch that again. So this is transform. Let me think about this. So any random point will be transformed to the stem, like the initial stem with function 1. Then I moved up a bit because I did transform 3 and then transform 4. So let me think about what this is doing. So what these guys are doing then is it's okay, let me just mess around with that a little bit. So what we did is we took the fern and we took this guy and we moved up. So we created like a leaf in here, and then we rotated over to create the leaf over here, and then we went up. Okay, so it looks to me like we are, one second. If you want to trace the central stem up without going into the leaves, then try taking the same shrink transform repeatedly. The other two transforms branch into leaves. Yeah, and since you can't see the structure of the leaves, it looks like random movement. Right, yeah, I agree with that. Instead of throwing the affine, okay. So one thing about the affine transform terminology is that I do find it rather intuitive. The affine transform seems to make more sense to me than, like, for example, just saying you're going to move halfway towards point 1, halfway towards point 2, and halfway towards point 3. Like, that kind of magics it up. But if you do the affine transform, then it's clear, okay, we're taking this point and then we're moving it into something that's in this area, right? So in some sense, I kind of wish that when we did the iterated function system video on YouTube, that we would have done it with the affine terminology. Like, that would have actually, I think, helped for understanding more. But we didn't. So, you know, we'll talk about it later, I guess. Maybe we'll do it this video. I'm not really sure. Okay, so let's see. Affine is intuitive, but how I learned this when I was like 5 from my dad was with a dice roll and halfway thing. Right. But that's the thing. Like, I feel like if you focus too much on like the halfway point, like the halfway functions, I feel like it does kind of come out like magic a bit. Also, Wikipedia article is looking a bit like a Rosetta code with snippets at the bottom. Right, but we don't need the code here. Like, at this point, we're trying to understand the math, not the code. Like, we have plenty of code and plenty of different languages that do this, you know? But I do agree with you. So, okay. Right, so we know what two operations do. So what I reckon we can do is we can just try out... Let me just try out two of them put together. So I'm going to try 2 different sets. So what I'm going to do next is I'm going to change order. Okay, so what I want to do is change the order so it's literally just 1, 2, 1, 2. 1, 2, 1, 2. Oh, I'm sorry, 2, 3, 2, 3. 2, 3, 2, 3. So these are the 2 functions that I'm having trouble with. So let me do include, G++, / Barnsley, because I know what the other 2 do. One creates a stem, the other one brings it up. You know, that's totally fine. The other 2 are the ones that I'm having trouble with, which are the structure of the leaves themselves. So, yeah. I just find it funny how blatant a style violation that is. Oh, I didn't realize it was a style violation. Yet to be known to me. Thank you so much for following, really appreciate it. MPV temp video.mp4. Okay, so we're gonna move this way and that way and this way and that way. Okay, does that make sense? Let's watch it again. So we move up and rotate, and then we flip around the stem essentially, and then up and rotate again, and then flip around the stem again. One second. Watch it one more time. So it goes up, over, up, and over. Oh, good. Yeah, let's take a look. From the mathematics articles should not include multiple implementations of the same algorithm in different programming languages unless there is an encyclopedic interest in each implementation. I guess. I don't really know what counts as encyclopedic, you know? Like, what, you know, I don't know. Okay, so I'm going to try something else now. What I'm going to do next is I'm going to do just 1, 1, 1, 1, 1 for the order. So let's do 1, 1, 1, 1. Okay. Include, I know what this is going to do, but I'm just double checking. Let's write that over here, run G, and /Barnsley. If the implementation in a specific programming language or paradigm is by its very nature notable. Yeah, I guess you're right in that it's probably not notable then for each individual language. 1 second. Okay, so now I'm going to run MPV. Okay, so it should just go up. And then it just keeps going up, doesn't it? There it goes. Okay. Cool. Just kind of leaves. That's fine. AKA the hex algorithm. So like fast inverse square root and C. Oh, right. Yeah, that's the one that people care about. The implementation of a specific programming language or paradigm is by its very nature notable. Okay. So what I'm going to do next is I actually don't know what I should do next. I could try 1, 2, 3. Let's try this. 2, 3, 1. Let's go over here and try writing this, and then compiling that, and then run MPV. Barnsley, and then MPV. I know which one you're talking about. You're talking about the one with the game. Yeah. So let's do. Yeah, I don't know why people are so into that one, but yeah, people are like super into that one. Which I guess is fine. Okay, so now we're gonna run mpv temp video.mp4. Okay, so we're gonna move up, over, flip, up again. What I want to do is have the Barnsley Fern behind it already. Now we're in the explicit C conversion from float to binary. Yeah, I've seen it before. But it's cool. Okay, so what we've essentially drawn. What does our map look like? Is our map just dumb here? 1 second. I think I want the world size to be bigger, I think is my issue. So let me make the world size bigger. But I think what we just drew was the following part of this guy. I think we just drew this, and then it flipped over to be... Yeah, I want to have the Barnsley Fern drawn in the background. And then if I have the Barnsley Fern drawn in the background, and then I put this other transform on top of it, we should see it's just a random distribution down here. And then it kind of goes up here. And then it flips, I think, over here and then down here. Let's rewatch what we had. MPV. So it goes up and then over there. Okay, so this corresponds to moving up and then over this way. So I think this goes from here to there, to this stem in there. And then, wait 1 second. We go back over here, flips over to the corresponding leaf over here. And then we bring it back up again to this leaf in here. Okay, I think I see how that works. But I need a better visual of it still. So, I mean, we could just do, we see what each transform is doing. That's totally fine. Hey, Prats, how are you? Basically, my point is that that's the bar you have to hit for a specific language paradigm. Yeah, I agree. Okay. What are we doing today? We're kind of just looking at the Barnsley Fern. It's an implementation of... It's another... Here, this is what it is. This is the Barnsley Fern. It is another tractor that is not the Sierpinski triangle. Is this playing? Now it's playing. You can draw it in a very similar way as to how you draw the triangle, in that you create basically a set of functions, and then you iterate through the set of functions in a weird way. So yeah, that's what we're working on today. So what I'm trying to do in particular is figure out how each of the transforms is related to the overall shape of the fern in the end. Let's see. I agree with what you're saying, that drawing the Barnsley Fern in Python and JavaScript does not change, or is not inherently novel. Okay. Is that the fast inverse square root algorithm based on some C specific? Right, that's the one, and not the properties of IEEE floating point standard used in most languages. As for the attractor, maybe try thinking of it like you would standard recursion algorithm. You ensure the set of invariants, and then you get only the thing that fit into those invariants. Do a color shaded map, cycle through each color spectrum for each dot as it gets transformed. If you really want to watch, make it wait for you to hit a key between drawing dots. Right, so the issue with that is that you need like millions of dots. Well, not millions, but you need thousands of dots before you actually start to draw the appropriate structure, in this case, a curved line with copies of itself branching off. So what I want to show is just, I want to have the Barnsley Fern in the background, and then after the Barnsley Fern is there, I then want to show this transform on top of the fern. That's what I want to show. So since we have the fern already drawn, and we have the random, distribution of points, essentially what I want to do is just like show each affine transform as it relates to the fern. I don't see how using bigger dots would help here. Like, you need to see the structure, you need a bunch of dots. That's just how it is. Okay, so we already have the fern being drawn. What we can do is we can return back that distribution of points. Yeah, we could also just, we could do a picture of the leaf. But I don't know how to do that. So instead I'm going to use the dots. I don't know how to do that in GathVL. I'm sure there is probably a way to put the image on there, but I just don't know. So I'm just going to use the dots that we already have and just draw that in the background. I think that's probably it's a bit easier, I think. Okay, so we do have Barnsley in here. So I guess what I want to do is maybe I create like a true false statement or a true false object or some object. I want a just true false variable, which basically says, hey, are you actually going to write this out or not? And then I just want to return back the vector of points in the end, I think. What project we're working on today? I just said it, but we are working on just basically trying to understand how each function of the Barnsley Fern corresponds to the drawing of the fern itself. So that's what we're working on. Okay, so at the end here, what I want to do is just return the points. Oh, I don't have the points, do I? I do not. Okay, that's fine. Yeah, of course I don't have a vector of points. Why would I return a vector of points? That makes no sense, because we have a lot of points. So the opera server is starting to get active again. Best of luck with the fractal. I've got a notional hyperfixation. All right, have fun, man. See you around. Good luck with the server. Okay, let me get some water. Actually, guys, I'm gonna be right back. Sorry about that. And then we'll keep on working on it in just a second. So 1 second, guys. Okay, back. Give me just a second, guys. I'll show my face again. I only have about maybe 20 minutes left on stream, by the way. I do have to leave before 6:30, which is when, again, the realtor is coming by with some people. I've been noticing that I am just incredibly not eloquent anymore in speaking. I don't know what has happened. I think it's probably because I just haven't been able to work out for the past 2 weeks or something. But I am just fundamentally unable to form complete sentences. And I don't know what the problem is with that. Simulating Fern's growth, is that what it's about? Yeah, so, okay, so the way this works is the same way in which, I mean, I don't know if you were here for yesterday's stream, but essentially they all work via this thing that's called an iterated function system. So the stereotypical iterated function system is the Sierpinski triangle. Here, essentially, you iterate through 3 functions, which is p plus a over 2, p plus b over 2, and p plus c over 2. And in doing this, just by taking a random point and kind of, going through these functions in a completely random order, you will eventually redraw the entire Sierpinski triangle, which is just a triangle of triangles and triangles and such. And so this triangle in this case is known as an attractor because it kind of attracts random points to it by going through the chaos game in this way. We went through a paper yesterday on exactly what that means, kind of going through the mathematical explanation of it. Sorry, also, I just, because of the way my microphone's set up, I kind of hit the cord for the microphone, so you might have heard something. But yeah, so the stereotypical iterated function system. The iterated function system for the Barnsley Fern is quite different, but it's kind of in the same vein in that you have these 4 functions, all of which do different things. So one function clearly will create the stem at the center of the at the middle of the visualization. Another one will just kind of bring that stem successively upwards and it kind of going in this direction, and that's totally fine. The problem I'm having is trying to understand the other 2. Which I think one of them will bring it to this point here. We'll bring it over to, will bring us to, this area of the leaf, and I think the other one will bring us to this leaf over here. So I think what we're doing is okay, so maybe what I need to do, is I need to keep track of multiple points at the same time and visualize those movements. Because I think what we're doing here is we're literally just okay, well, let's just take a look at the transforms one more time. So anyway, that's where we're at. I'm just trying to figure out what the other 2 do. So one, again, brings us to the stem. The other one brings us successively upwards. So the other 2 must in some way create the leaves. And I think one will create a leaf on the left, and the other will create a leaf on the right. The problem is that's kind of contradictory to what it says on Wikipedia, and that's why I'm kind of struggling with it a bit. I know that these visuals do, what they're expected to do. You know what? One thing that we could do to make this a bit easier. Yeah, I know what we should do. Okay. Yeah, no, I know exactly what we should do. We should create a function that twiddles. We should create a twiddle function. I don't know what this is called, but a function that basically modulates all of the different variables here. So what we'll do is we'll just say, look, each of these functions has, 3 variables that we can increase and decrease. And what we're going to do is play with each of these variables, and this will allow us to understand what each function does. And I think that's what we're going to do. Came to your stream, learned something new? Cool, glad you learned something. Sorry that I'm kind of rushing through it as well. Again, I don't have too much more time available in today's stream. Literally, just, again, 20 minutes or so. And then I unfortunately have to go because I have to prepare for the people coming in, and I have a few messages I have to respond to. It's just a busy time in my life right now. But hopefully tomorrow I'll be able to do a much longer stream. So I think what I'm going to do now is I'm actually going to go ahead and start making the twiddle visual is what I'm going to call it. It's just what I'm going to call it. Barnsley twiddle is what we're going to call it. I always look up the page you're reading. Yeah, so let me give that to you, by the way. Yank, yank. Paste this over here. So I'm now going to do the Barnsley twiddle function. So void Barnsley twiddle. Okay, so this is going to take in a couple different things. It should take the camera, ampersand cam. It should take in the scene, ampersand world. And the last thing I think it needs to take in is just int n, which is going to be the number of points that we are that we're going to be drawing. So my point is I want to draw a kind of small version of the Barnsley Fern. And then after drawing the small version of the Barnsley Fern, what I want to do is just kind of move the variables around and see what happens. So I'm going to keep maybe 1,000 or maybe 10,000 points in memory. And then after we have those points in memory, we're then gonna, we're just gonna mess around with each variable. So the article that I'm talking about in particular is the, let me go to the algorithm archive now. Let me go to affine transformations. Where are we? Here. So what I want to do is a visual kind of like one of these guys. So let me just play this. So as we modulate one of these variables in here, we see that the overall visualization changes as well. So what I want to do is kind of make this visual, but for each of the transforms in the Barnsley Fern. So we're going to like, well, okay, we have 4 different transforms. Let's just modulate each of these transforms, and this will explain what each of them do. Because clearly this visual of like taking random points and moving them about didn't really lead us to anything. So I might just do it this way, because I think this will help us out in the end. But yeah, if you haven't seen this chapter already on affine transforms, I would recommend it. I think it's actually pretty good. Of course, I think it's good because, you know, I made it. But I spent a long time on this chapter, a super long time. There's also a video available on YouTube if you're interested on affine transforms. But yeah, I spent a super long time on this video explaining like rotation matrices and like, you know, how to scale and what all these things mean, shearing, all this kind of stuff. Spent a long time on it. Okay. Close that for now, and let's think about this. So the other thing we want in the apply Barnsley, or the Barnsley twiddle, what did I call it? Twiddle, yeah, Barnsley twiddle function, is we want to explain somehow what function we're twiddling and what transform we're twiddling. So each function has 6, you know, like things that we can, 6 dials that we can move up and down. So what I'm going to do is, I guess I'm going to call it function number, fx number, and we're going to call this an integer, fx num, and then finally we want an int, which is going to be affine number, a number, and I'm just going to put it up here in the comments. So this function will create a Barnsley Fern, Fern every iteration, I guess. Barnsley Fern, and then change the Fern according to the selected function number and affine transform form within that function. That barely fits on the line. That's okay. Okay, so here we're going to say fx number. I'll get to that in just a second, River. fx num is the Barnsley chosen Barnsley function. One second, function. And then a number. I don't like the name here, but a number is going to be equal to the affine transform within that function. Okay, 6 possible. And in here I'm going to say 4 possible. Oop. 4 possible. So River, just hopped on. How are your feet doing? Way better. I should be able to do the workout stuff tomorrow, actually. Pretty excited for that. I think honestly, like, I have not been able to like form a coherent sentence for like the past few days. Like every time I'm in a meeting with someone, like I'm constantly stuttering and I'm having like a hard time just like finishing sentences. I've had like a constant headache and like a constant stomach ache as well. And I think it's just because I haven't been like as active as I normally am. So I'm really looking forward to being active again and just like, you know, doing my workout routine and stuff like that, because it is tough. I do not know how people have the like. I don't know how people have the, how do I put this? The, like, I don't understand how people are, like, motivated enough to not work out. Does that make sense? That's a very bad way to phrase that, but, like, I just feel so tired. You know, like, constantly, incredibly tired. It's like, how do people live like that? Oh, I sound, like, so, like, elitist in saying that. But you know what my point is? Like, it's just, it feels, like, bad. Anyway. Let's keep going. So, I'm only gonna be able to stream for like another 20 minutes or so. I said that I'm only gonna be able to stream actually for another like 10 minutes or so. So just letting everyone know that I'm gonna try to just kind of like create like an outline of this function, and I think tomorrow we're gonna come in and actually like write it. So, let's see. Let's go ahead and write down stuff that we know we can do. So here, what am I gonna do? I know that we want to. I know that we want to encode everything, so we're going to grab this encoding section and put it in there. So let's grab this, paste it there. Okay, what else are we going to do? What I want to do next is probably we do want to create a vector of points. And then, yeah, so probably we want all that as well. So let's go in here and grab this guy. Okay, and so now essentially all we want to do is in here, we're just going to do chaos game. Game with functions and chosen. Okay. Parameters. So probably what we want to do is do chaos game is going to be down there, and then up here we're going to do change function. Create function set. Okay, so here's where things are probably going to be a bit different. So let me go up here and let me think about this really quick. So the way I have this right now is I have this vector apply Barnsley, which will basically say, you know, we have some sort of point that we're reading in, and then we have a Barnsley ID, which is the ID of the transform that we're going to do. It's going to be 1, 2, 3, or 4, right? So my question is, am I going to be able to modify this function, or should I basically recreate this function for this weird like affine search through everything? I think what I'm going to want to do, is create my own set of functions for this Barnsley twiddle function. Yeah, let me get some water. I don't think I'm going to be able to get into that right now, because I think I should probably go. Again, I need to be out by 6:30, and then I have other things that I need to do before that. So I think I'm actually going to run for now. But I think tomorrow what we'll do is we'll come back, and we're going to just try to implement this Barnsley twiddle function and see what we can do with that. So I think we'll close for now. I'm going to, after stream, take some time to kind of try to get through that paper that we were reading through yesterday again, and just do some stuff there. So I think this is it for today. We're going to come back tomorrow, hopefully do a long stream. I've got a lot of like chores and stuff that I have to do in Boston tomorrow morning. Like I've got like 3 or 4 things that I need to do, and go from there. So the paper I mentioned, I know I downloaded it, but I don't know. Okay, let me try to, let me do the following. Let me go here. I'm going to go to downloads, and then I'm just going to do, can I sort the downloads here? I don't think, okay, let me try this again. So let me do cd downloads, and then we're going to run ls history grep ls. Let me grab the appropriate paper. I type ls a lot, don't I? latr. So ls latr, and the one I'm looking for, is it on the convergence rate of the chaos game? That's probably it. Oh no, I know which one it is. It's Ocular 2007. That's the one it is. How long is the chaos? Oh nope, that's not it actually. Nope, 2102. Ocular 2102 maybe. Calculating box dimension with the methods of types. Is this it? No, that's not it either. Maybe it is on the Ocular on the convergence rate of chaos games. This it? Oh, this is it. Yeah, 3rd of February 2021. Let me Google this and give that to you. So this is the paper we were going through yesterday. This is kind of like the same question that we were asking. You can find it on the archive as well, but I think this will let you download it just fine. But the point is that it's basically the question of like, you know, how attracted are you to the Sierpinski triangle? That's the same question here. It's like, you know, how do you know how far away you are from the attractor at any given point? And that's the question that we were trying to answer. Let's see, how many people do we have watching? We've got 18 people watching. I might just not raid anybody, because the issue with raiding people is like every time you raid somebody, you know, they then ask in chats like, how's your stream and stuff like that, which is totally fine. Like, it's valid. I do the same thing. But I don't really have time to answer those questions. So no raid today. Gotta go. But I will talk to you guys tomorrow with hopefully a bit of a longer stream. Unfortunately, tomorrow I have to leave at 5:30. So like when I say a longer stream, I'm hoping to stream from like noon to 5:30 is essentially what I'm hoping to stream tomorrow, but we'll see. And then the next day I'm not able to start streaming until 4. Like honestly, I just don't have time to stream this week. But I'm trying my best, so we'll see how it goes. And that's it for now. So thanks guys again for watching, and I will see you next time. Bye guys.